let's get started. How did everybody's first submission go for the project? Well, okay, good. Still working on getting, my goal is to just update all the attendance. Like I've been a little behind on updating the attendance grades and whatnot, but I'm gonna, after today, I think I'm just gonna do them all at once. Homework 5.6 and 5.5 are still being graded. I don't have an additional homework for you today, just the homework 5.7 that's due Monday, okay? And hopefully that one's pretty short, given the discussion that we had last time on frames. So just so you are aware, a couple things. So I'm going to assign 6.1 that's due, that assigned Monday, due Wednesday, but homework 6.2, I'm going to give you an extra lecture on. Homework 6.2 is a little long, and it's actually worth double because it's a big assignment. There's no real way I can get around it just because of the nature of the problem, so I'm going to give you more time, and because it's a lot of work, I'm going to give you more credit for it. In fact, what I'll do that Friday is I'll give you some, like our lecture will be, I guess what I call Dr. Mike's tips and tricks for making that analysis easier. So, but that's running before we're walking. Let's start walking today with deflections on beams and frames. Any discussion on or questions on logistics? All right, one thing I'll plant a seed before we move on. So I guess I would call this module 6 is deflections on beams and frames. After we finish module 6, we're going to get into module 7, which is software analysis, okay? So we have a particular software program that we're going to use in here. I have my homework 6.3 is just you installing the software and uploading proof that you did it, okay? But after that, we're going to come to class and we're going to be doing that software. We're going to be using it together, okay? So just make sure that you are aware of that. The software that we are using is both Windows and Mac friendly. So you shouldn't have an issue with whatever laptop that you use. So I switched it up just for the Mac users. So that, and it's a software that is written with, it's written in MATLAB. You're not using MATLAB, but it's based off MATLAB. And part of me gets a slight chuckle when I mention the word MATLAB to civil engineering students, and it is akin to mentioning garlic to vampires. You all, it's kind of funny. But you're not using MATLAB, don't worry. So it's just that they use MATLAB to write the program. So, okay, enough about that. Let's get into our topic today. Let's discuss deflections. Okay, so we're going to be discussing deformations in beams and frames, and we're going to be using the method of virtual work, just like we did last time. But it's a little different in terms of its applications, and there's a couple things that we kind of need to be aware of. We also need to derive some conversion factors for our units that we use in typical imperial units. So let's go back to trusses, okay? Because the framework's going to be the same fundamentals, the same theory, for the most part, is going to be the same. The mechanics are a little different, but the general idea is the same. So if you have the displacement, if you have a problem where you want to compute the displacement of a truss joint, and I'm saying use typical USCS units, okay? So this is our formula, right? We sum the little f's times the big F's times the L's divided by the E's divided by the A's. And we do that calculation for every member in the truss, and we sum it up, right? Y'all remember that? So what do these represent? Well, first off, just in general, this quantity that we're summing for every member is the energy stored inside every member. Remember, we have the energy in, or the energy done to the system has to equal the energy that the system is storing. And so what we're doing is we're summing up the amount of energy that the system is storing. And that's going to be set equal to our deflection. In order to do that, we do two analyses, okay? We do the analysis with the original loads on the structure, and we call that big F. And then we do the analysis for the virtual structure, and we call that little f. What is the virtual structure? We kick all of our original loads off the structure, and we place a single unit load at the point of interest with a magnitude of 1 in the assumed direction of the displacement. So if we get a positive answer, that means our assumption was correct. If we get a negative answer, it just means it's deflecting in the opposite direction, okay? And that is going to be a little more possible with beams. So like when we do rotations, you might assume that it rotates one way, in fact it rotates another. So that's not that unheard of, okay? Just keep that in mind. All right, now one of the things that we did need to mention is that this formula is blind to units, right? Okay, so whenever we compute our energies, we need to compute the length. We need to use the length of each member, and the length needs to be expressed in inches, right? Do we typically express truss elements lengths in inches? No, we typically express them in feet. Would that make sense? So just for sake of discussion, could I develop a USCS conversion factor for trusses? That's going to bug me. And I'm going to say that it's 12. Okay, why 12? Because if I were to just use the raw dimensions of the truss, the real forces in kips, the lengths in feet, the E's in KSI, the areas in square inches, if I did that, okay, my answer would be wrong. I would need to, if I used the raw base units, I would need to multiply my final answer by 12 to get everything to make sense. Is that a fair point? Now, we didn't do it that way when we did truss analyses. Instead, all we did is we said, you know what, let's just convert the member lengths to inches and just multiply everything directly. It was a little easier, okay? We're going to do something a little different for beams. We're actually going to develop a conversion factor for beams. Well, actually, two conversion factors. But I just want to plant that idea in your head that we're going to need to develop a conversion factor to get our units to make sense. The conversion factor is a little bit more involved in how we get there. Now, remember that, again, what we're doing when we sum those terms is we're summing up energy components for both the external work done and the internal stored energy. And so, in order to resolve the problem of only being able to compute external work where there is a load, the answer is we'll put a load where we're interested in finding the deflection. So we'll put this fake load P1 that's sort of like a marker that helps track our energy. We'll put that on there first, then we'll stack the original loads on top of it. So we get 3 different energy terms of external work and 3 different stored energy terms. But each of those pairs, each of those corresponding pairs have to equal one another because energy can't be created or destroyed. So we'll just use the easier ones, the most convenient ones that make our life a little easier, and then we set P1 equal to 1, and boom, there's our method of virtual work, and that was it in a nutshell. The only thing that I want to discuss before we get into beamland is just a note on constant forces versus variable forces. I talked about this last time, but I don't think I fully closed the loop on it. So ultimately what we're doing is we're summing the energy in every member, and so this is what we're doing when we compute truss displacements. We're summing up the stored energy inside the member, and we're summing up that U2 term, which was the little f times the big F times the L divided by EA. But when we did that, that definition only works assuming that the loads are constant. Well, actually, it's not just the loads. It could be the loads. It's also assuming a lot of other things are constant. For example, it's assuming that the area is constant. For example, what if I had a truss member that looked like this, that got bigger on one end than it did on the other, right? That formula wouldn't work because the area would vary along the length, okay? So in order to resolve that, if we have something that's variable, if we have a load that's variable or maybe an area that's variable, or theoretically we could have an E that's variable, although mechanically that'd be really hard to kind of imagine. But the idea is that what we're doing is that if we're integrating, what we're doing is we're still summing up the energy, but instead of summing up the energy for the entire member, we're just summing up the energy for each differential element. So what we'll do is we'll say, okay, the stress is F over A, the Hooke's law says stress is E times the strain, and the strain is just the change in length over the original length for each element. So we'll rewrite our terms and we'll sum them up, but summing them up just means integrating. So what we're going to get is this. So we'll get a sort of a small increment of energy, which is just going to be, you know, the load times the load over EA, and we'll integrate, and we'll get this, okay? So all this, the difference between this and this, the only difference is that if we have a situation where we have variable loads, or maybe variable areas. Now, one thing I'd like to close the loop on is if we look at this definition, does this definition still work if everything's constant? So what I'll say is if f of x and f of x are constant, what happens? So we get the integral from x equals 0 to x equals L of little f, big F over EA, right? So let's go back to Calc 1 land. So if all this is constant, I'll factor it out. Let's go back to Calc 1. What's the integral of dx? Remember that? X. It's like the integral of 1. What's the integral of 1? It's just x. So we have little f, big F over EA times x evaluated from x equals 0 to x equals L. And how do we do that integral? We plug in the top number minus plug in the bottom number, right? So we get little f, big F over EA, L minus 0. And what does that equal? It equals that, right? So the point I'm making is that this definition is just a generalized extension of this if we have variables. That's all that is, okay? And what's the pattern? Well, if everything's constant, so let's look at the pattern. So let's look at the pattern. If everything is constant, we have a virtual response, a real response, a length, and then some constitutive properties, okay? If the response is variable, we have a virtual response, a real response, some constitutive properties, but we integrate. The L vanishes, and instead of L, we're just integrating along the length. Does that make sense? If you understand that pattern, then what we do for beams is no more complicated. It's really the same story, okay? Maybe executing it is a little trickier because we have to actually do some integrals, but it's not that bad, okay? So let's talk about beams now. Let's actually focus our discussion on beams. And the first thing that we're going to do is we're going to look at the mechanics of beams. So everybody in here should have had Engineering 216 last semester, and I don't remember how it was presented, but I know you saw this, so I want to go about looking at the differential equation for beam deflection. Don't worry, we're not solving differential equations. We just need to set the groundwork, okay? So I want to begin with a quick review of some section properties. So we're going real basic here, okay? So let's consider a function that is bound by the x-axis between A and B. So how do I determine that area? Real basic. I integrate, right? So we can define the area under the curve as the integral from x equals A to x equals B of that function with respect to x. Pretty easily, right? Now, what I'm going to do is I'm going to start using some shorthand notation. So instead of writing all of this, what I'm going to say is I'm going to integrate over the region, so integrate over A, and instead of f of x times dx, I'm going to say I'm going to sum up all these dA terms. dA is just a little bit of a differential element of area. I'm just summing that up over the region, okay? The reason I'm going this basic is because when I start throwing some other notation here in a bit, you'll see where that comes from, okay? So the reason I like this notation is because it makes it easy for us to define moments of area. So here I have the area under the curve as the integral of, or the sum of these dA terms. I can now define moments of area really easily. Now in calculus land, how do we define the moment of a function? Well, the moment of a function is, so if the area is the integral of dA, then the moment of a function is the integral of x dA or y dA, okay? So first moments of area would be the integral of xdA or ydA. And we can use these to compute centroids. So for example, if we take the integral of xdA divided by the integral of dA, so remember, whenever you think integral, I kind of want you to think sum. All this is sort of like a sum of XA over a sum of A. Y'all recognize this formula? That is a centroid formula, right? I hope y'all did that in statics, right? Maybe y'all had me for statics. I know we did that because I know we did that because I taught you how to do it. So this would be our method of computing centroids, right? So what I have here on the screen, these are first moments of area. Why do we call them first moments of area? Well, because if we instead change this from x to x squared, we have a second moment of area. Instead of y to y squared, it'd be a second moment of area. Okay? We tend to see the second moment of area show up a lot in mechanics. So we have a very special name for it, and we call it the moment of inertia. Okay? That make sense? So if you ever hear me use the term moment of inertia, really all I'm talking about is the second moment of area. I'm taking dA, multiplying it by x squared, and I'm just integrating over the region. That's all the moment of inertia is. So when you take a rectangle, anybody remember what the moment of inertia of a rectangle is? BH cubed over 12. 12, right? So what is BH cubed over 12? It's just taking a rectangular region, integrating the region times x, or in that case, y squared, right? Because it's the moment of inertia with respect to the x-axis. Why are these flipped? Why are the subscripts flipped? Because if I have some region, so if here's some region, and here's a coordinate system, so y, x. So the question is, why are these flipped? Well, how far is it from some point? How far is it from there to the x-axis? How far is it? It's y. Right, so that's why, if you look here, you see like qx is the integral of y dA, or qy is the integral of x dA. Why is it flipped? Well, the distance from the x-axis is y. The distance from the y-axis is x. That's why it's flipped like that. Don't worry, we're not going to have to go too far down the rabbit hole with this. I just want to make sure we're all on the same page. So, the only other thing I want to mention on the math preliminary side is how to compute the curvature of a function. Now, you all have been given a function, let's say. How do you compute the slope of that function? If I give you a function, how do you compute its slope? How do you derive a function that expresses its slope? The derivative, right? So if I give you a function, the slope of that function is defined by its derivative. How do you determine the concavity of a function? Somebody else. If the slope is defined by the first derivative, how's the concavity defined? The second derivative, okay? So just to make sure we're on the same page, so the slope is defined by the first derivative, the concavity is defined by the second derivative. Does anybody remember how you define the curvature of a function? It's okay. I bet that I didn't remember it when I was in your shoes, and I really don't expect you to. I promise you, it's in your calculus textbook. If you open your calculus textbook, go into the index and find the curvature of a function, it's defined by this mess. Don't worry, we're not going to use this mess. But the idea is that the curvature of a function is defined by the second derivative over all this hullabaloo on the bottom, okay? What we're going to do is make a real simple assumption with it, but I'm just going into MathLand to tell you that the specific definition of the curvature of a function is defined by this. A lot of times what you'll see in MathLand or in MechanicsLand is we'll take the reciprocal of this, and if this is the curvature, the reciprocal of it is called the radius of curvature, okay? The reason why I bring this up is because when we write our differential equation for beam deflection, it has a lot of names. Sometimes it's called Euler-Bernoulli theory. Sometimes it's called the moment-curvature relationship. So that's why I bring this up. Okay, everybody with me so far? Okay. All right, so let's talk about beam deflection, and let's talk about our assumptions. Now, the mechanics of beams are a little different than axial members. So we have to make some basic assumptions. So while the mechanics are different, the assumptions tend to be pretty straightforward. The first thing that we're going to assume is that the behavior is linear and elastic. So elastic behavior means that if I apply a load, it deforms. If I let it go, it goes back to its original shape. That's what elastic behavior means, that there's no permanent deformations. Linear behavior means that the stresses and strains are proportional. So for example, if I put 10 kips on something and it deforms 1 inch, what happens if I put 40 kips on it? It deforms 4 inches, right? It's a proportional relationship, right? It's linear. That's what linear and elastic means. Okay. The other assumption that we're going to make, and this one's a little more nuanced, but the other assumption that we're going to make is we're going to assume what's called small deflection theory. Okay. Now, small deflection theory is sometimes a little bit of a hard idea to understand, but here's it in a nutshell. Okay. So here's a beam. I take a beam and I put load on it. It deforms, right? It's going to deform something like this. Okay, so let's think about this from a structural analysis perspective. So let's say here's the beam, let's say it's simply supported, and I put 20 kips in the middle. What are the reactions on either one of my hands? Up, and how much? 10 kips, right? Okay, so when you do that analysis though, you assume that the structure is rigid. You assume that the structure does not deform, right? Okay, well the structure actually does deform. It does deform a little bit. What small deflection theory means is that the equilibrium of the structure is not affected by the deformations, okay? There are problems in structural engineering where we do have to consider that effect. We call that large displacement theory. I'll give you an example of large displacement theory. So I'll give you a funny example and then a more real world one, okay? So let's say that I am standing on top of a really high hill, on the very apex of the hill. And Ethan doesn't like me very much, and he decides to shove me, okay? So if he shoves me, I might be able to catch myself. But would you agree that it would probably be easier would you agree it would be more difficult for me to steady myself if I was wearing an 80-pound backpack? It would be a little tougher, right? Now, why is that? Okay, so I'm standing on the hill, okay, and I've got this 80-pound backpack on, and normally I kind of like to stand like this where the backpack is in line with my center of gravity, right? So what happens is Ethan shoves me. He shoves me, now the backpack is off my center of gravity, right? So what happens is, because it's off my center of gravity, it's causing a moment that wasn't there before. Force times a moment arm, right? That moment arm causes more deformation. That deformation causes more moment. That moment causes more deformation. And see how it sort of builds on itself? That is a large displacement problem, right? And so it sort of builds on itself and you get that whoa, 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 whoa. That's what large displacement theory means. There are some problems in structural engineering where we have to consider large displacement theory. A good example of those are wind and earthquakes, okay? So for example, you have a building that has a very large vertical load and suddenly it gets hit by wind or it gets hit by earthquake and that load gets shifted over, and so the exterior columns, for example, that are keeping the building upright laterally have to consider those second order effects. But those are one component in a vast structural system that most of those elements don't have to worry about that, okay? There are provisions in design land where we can handle second order effects a lot easier, but I just mentioned that to sort of explain what small deflection theory versus large deflection theory means. Does that make sense? So for most deflection problems, we're going to ignore the second order effects. That's what second order, that's what large displacement theory means. Okay. So what I'm going to do is now I'm going to get into mechanics land and I'm going to look at a deformed piece of beam. So here's my beam and I've got loads on it. So let's say it deforms, so it deforms something like that. I'm going to sort of look at a segment of that beam and see what's going on. So I've got this. Now, if you had to come up with a really basic idea of what this shape looks like, it kind of looks circular, doesn't it? Looks like a circle. Well, do you all remember that the length of an arc can be expressed as the radius times the subtended angle? Y'all remember that? That if here's the radius and this angle is 20 degrees, the radius times 20 degrees in radians will tell you that curved length. Y'all remember that? Okay. Well, I propose that that formula only works along the neutral axis, along the centroid of that beam. Away from the beam, or sorry, away from the neutral axis, we get a deformation. So for example, looking at this image, so the solid line, I propose the solid line that the length remains unchanged before and after deformation. But this dashed line, it got shorter. Okay, and how much did it get shorter? Well, it got shorter by, if this is rho theta, this is rho minus y times theta. Okay, so now what I'm going to do is if I have an initial length and I have a final length, what I'm now going to do is try and compute strain. Do y'all remember the shorthand definition for strain? It is the change in length divided by the original length, right? So if I take L final minus L initial and divide that by L initial, I'll get the strain. So that's all I'm going to do here is get the strain, take the strain, multiply it by E to get the stress, okay? There's a lot of algebra here, but that's all I'm doing, okay? Don't worry, I'm not expecting you to have to do this derivation on your own. I just want you to kind of understand where I'm going with this. Everybody with me so far? So what I'm doing in this first part of the derivation is I'm trying to say, okay, what is the stress as a function of how the beam is deformed? And then on the other side of the derivation, I'm going to say, well, what is the stress as a function of the loads that we're putting onto it? Then set those two equal to one another, and I get my expression. That's basically it in a nutshell. Is everybody kind of following along with me on this? If you need me to stop, you tell me. Like, everybody good? I still see a couple people writing. I'll give you a sec. That's fine. Everybody good? Okay. So this is the stress looking at the deformation. What about the stress from the forces? Okay. Well, now I want to look at the stress on the other end. And I'm going to look at it in terms of moment. Do y'all remember this in mechanics of materials, or mechanics of deformable bodies, I should say? That at the neutral axis, the bending stress is 0. Then as you get away from the neutral axis, it either experiences compression or tension, right? So here's my little beam. I bend it. The top is smushing together, so it's being compressed. The bottom is being yanked apart, so it's in tension, right? So at the center, we have 0 deformation. As we get away from this, we get compression or tension, right? So what I can do is I can say, you know what? Let's look at each little slice in the beam. Each little slice is going to have a force in it. The force in that slice is going to be the stress times whatever the area is, some little differential element of area. Okay? I'm going to take that force, multiply it by a moment arm to get a moment, and then I'm going to integrate that, and I'm going to integrate that, and I'm going to get the moment across the cross-section. Okay? Now, there's a negative result. The negative result is just to accommodate our sign convention. So when we look at bending, we consider smiley face positive, frowny face negative. So just to get the math to work right, we have to throw a negative in there. That's where that negative comes from. It's not really a big deal from the derivations perspective. I'm trying to be specific. So now I've got the moments as a function of this stress. I'm going to take what I had on the previous slide, plug that into my stress formula, do a little bit of algebra, and I wind up with this. I get E divided by that radius of curvature times the integral of y squared dA. What is the integral of y squared dA? It's the moment of inertia, right? Remember, that's the second moment of area. So what I'll do is sub that in, and I get this. Okay? So the only thing left to do is to use that curvature differential equation, and now I'm rocking and rolling. Okay? I still see some folks writing things. Are we good? Okay, now, so here's where I'm at so far. I've got my moment equals EI divided by that radius of curvature. I'm going to rewrite that using the remember the radius of curvature. If I reciprocate that, I get the curvature. So I get the curvature is m over EI. So this is what I mean by the moment curvature relationship. That moment over EI equals the curvature. Okay? Well, here's the thing. Remember that curvature expression and how it's kind of nasty? Okay, let's go back to small deflection theory. So if you take deformations that are really small, so we're talking about a beam that goes from really straight to like that, like really small deflections. Small deflections, so if I have small deflection, how much do you think the slope of these lines are? The slopes are really, really tiny, right? So what happens if you take a really tiny number and you square it? You get a really tiny number, right? So what do we do here? We'll just say that this whole denominator is 1, and instead of dealing with the second derivative divided by all this hullabaloo, we'll just say the curvature is the second derivative. So we take all that mess in Calc 1 and make it a lot easier. And instead of moment over EI equaling curvature, we say moment over EI is the second derivative, and we get left with this. This, ladies and gentlemen, is one of the most fundamental equations in all of mechanics. That the expression for beam deflection. That the second derivative of deflection is m over EI. Okay? Again, very fundamental in the land of mechanics. Now we're going to use it here a bit, so don't worry. Now let's use it and make our lives a little easier. So far, so good? Okay. Now let's talk about the method of virtual work. Okay? So the method of virtual work for beams, we're going to look at displacements and rotations. Okay? So just to be clear, whenever I have a beam and I take that beam and I deform it, let's deform it like kind of silly like. Let's do this. Okay? So here's the beam and it's deformed. So if I'm looking at, let's say, this point on the beam, not only has that point displaced, like it started here and it went down, not only has it displaced, but it's also rotated, okay? It's gone down and rotated a bit because the slope of that line's like right here, it's not flat, it's down a little bit. So we're going to be interested in computing both displacements and rotations, okay? But the method is the same for both of them, okay? So let's show you how this works. How does virtual work change for beams? How does it change? Okay? Now, remember, in the method of virtual work, we analyze two structures, okay? We analyze the real structure that has all the original loads present, okay, which we're going to do, and we're going to analyze the virtual structure. How does the virtual structure work? We kick off all of the loads that are originally on the structure, and we replace it with a single unit load at the point of interest, okay? For the external work, what we do is if we're interested in dealing with displacements, we simply just put a unit load where we're interested. So what do you think we do if we're interested in rotations? If for displacements we put a unit load, what do we do for rotations? A unit moment. We put a unit moment where we're interested in. So other than that, nothing changes, okay? Same process, right? We just now, because of beams and their inherent nature, we have more displacements that we're interested in. And to be clear, we are interested in both in a variety of contexts in real world applications. So for example, if we're looking at the beams in this building, not only do the beams in this building have to be strong enough to supply to supply the capacity necessary to not, fail the floor system, but they also can't deflect too much. For example, a common deflection limit in building design is L over 360. Now, I'll tell you where that limit comes from. How many of you have ever been in a house or a building that had a plastered roof? Like plastered roof. How many, like old roofs have plaster on? So the idea is that if the beams start to deflect more than L over 360, you'll start to crack the plaster. That's kind of the idea. That doesn't mean that the beam's going to fall down and kill somebody, but obviously we don't want to crack the plaster. So that's, for example, where some of these deflection limits come from. Deflection limits tend to come from serviceability criteria. Not that the structure will fall down and kill people, but that it won't perform its day-to-day intended functions. So not only do we have displacement limits, but we also have rotation limits in certain contexts as well. When we're designing bearings for bridge supports, they can't rotate. They have rotation limits as well. So, but just random factoids for you. Okay. One footnote is that we assume a direction. If we get a positive answer, we assume correctly. No different than before. Okay. What really does change is this. Okay. The reason that this is different is how many moment diagrams did we draw that were just flat? None of them, right? They're going up, going down, they're parabolic, they're linear. The moment varies across the span. If the moment varies across the span, then we have to integrate to find the energy. That's why I was going on and on about this, that if we have variable loads, we have to integrate. Well, with beams, we do, because we have moment diagrams that go up and down, okay? So we have to integrate because moment changes as a function of x. Do you remember that assignment with Excel where I had you all derive the function? Guess what? We're going to have to do that a little bit more because we have to derive the functions in order to integrate them. Fortunately, the integration is really easy and our calculator can do most of it, but the actual derivation of the functions, that's where the work comes into play. So the way that, theoretically, the way that this works is we're going to determine the incremental rotation of each element and then sum that up. So let me show you how that works. So each element is going to rotate a little bit, and so the energy in each element is the moment times that incremental rotation. Like before, it was times that incremental displacement. Now it's times that incremental rotation, and so we just sum that up. So we set the external work equal to the stored energy. Remember, the external work is 1 times delta. We chose 1 because we didn't want to have to deal with factors, and so boom. So again, same idea from here to here, right? If the moment was constant, then our energy would be ML over EI. But the moments aren't constant, so instead of multiplying by the length, we just integrate, along the span. And that's basically it. That's our nutshell analysis. And remember, the format is very similar. Remember, the denominator here was a constitutive property, E times A. The denominator here is E times I. Okay, that's really the only difference. Why I? Because we're dealing with beams. We're not dealing with axially loaded members. Okay, make sense? Okay, so here's our summary of virtual work for beam deflections or beam rotations in a nutshell. So we have our moment functions. And we have moment functions from the real load, we have moment functions from the virtual load. And don't worry, we're not going to have a homework assignment on this until next week because we need to take some time to digest all this and apply it. For those of you that are thinking, oh my goodness, there's all this calculus, don't worry, it's a lot easier than you would think. So we have a set of real moment functions and we have a set of virtual moment functions. Where do our virtual moment functions come from? We kick all the loads off the structure, we place a single load at the point of interest, with a magnitude of 1 in the assumed direction of the displacement. And so this process works whether we're looking at displacements or rotations. It doesn't matter. It's all the same. We have our Young's modulus. We have our moment of inertia. And we just plug and chug. We are going to have problems where we're going to have multiple integrals. We just evaluate each one and sum them up. It's not hard to integrate. It just takes a little while to set up. Okay. I'll give you all a sec on this. This is going to be one of those like formula sheet pages, if I've ever seen one. No worries, this is important stuff. Now, before we move on, does anybody see a problem that we haven't yet discussed? I'll give you a hint, and it involves the captions in blue. Bam, bam, bam. Anybody see a problem? Different units. The units don't match, right? We have moments in foot kips, but we have moduli of elasticity in KSI and moments of inertia in inches to the fourth. We need to resolve our units, okay? It's the one thing left to do. So how do we resolve our units? We're going to derive some conversion factors. Let me show you how that works. Okay, and the cool thing is we don't have to derive different conversion factors for different problems. As long as you use a consistent unit system, you can use the same ones across the board. Okay, we're going to do some examples next week, but before we jump into that, I want to take some time and look at this first. Okay, so I want to start off with the original differential equation. Okay, so the original differential equation says the second derivative of displacement is m over EI. Okay, now if I want to determine the slope is the first derivative. With me so far? Okay. So the slope is the first derivative. If I want to get from the second derivative to the first derivative, I integrate, right? Now, let's just let me ask you a question, okay? If I have a function that's, I don't know, x squared, and I integrate, what do I get? Top one problem, what do we get?
X cubed over 3.
X cubed over 3, right? Now that is not affected, like, so what if I put a 9 right here? What do I do with this? I multiply by 9, right? So whatever is in front of this function, whatever constant, the constant doesn't affect the order of the answer, right? Okay? So let me ask you this. What if I integrate, I don't know, 15x to the 7th dx? What do I get? I get 15 over 8x to the 8th. But with me so far? Okay, so the point I'm making, let me show you the point I'm making. So here we have x squared, and we integrate, we get one level higher, x to the 3rd. We have x to the 7th, we integrate one level higher, we get x to the 8th. Okay? I propose from a units perspective, since we're integrating with respect to x, if the units for this are m over ei, then the units, from a unit standpoint, when we integrate, the units are going to be times length. We're going to have one more length unit on the slope, right? And if we integrate one more time to get the deflection, we're going to have one more length. I'm not saying this is the answer. I'm saying from a dimensional analysis perspective, we're going to have one more length unit down here as well. Does that make sense? Again, I'm just looking at units. So far, so good? Okay. So if that's the case, let's see if we can work out how these conversion factors would work, okay? Now, in order to work out how these conversion factors would be configured, we need to ask ourselves what our target answers are, okay? So what do I mean by our target answers? So if I was looking at a beam and I wanted to know how much it deflected, like here's the beam, I put some load on it, it deflects. In typical US units, what do you think I'd want to express that deflection in? Inches. Makes sense, right? Okay. What about rotations? Degrees. Right? We could do it in radians, but degrees might be a little more handy, right? Because radians can get kind of small. So let's look at our inputs. So forces, we tend to put in kips. Member lengths, we tend to put in feet. So let's follow along with that. So like our distributed loads would be in kips per foot. Moments would be in foot kip, right? We take moduli of elasticity, we typically put that in KSI. We take moments of inertia, we put that in inches to the 4th, okay? So I don't want to advance that just yet. But let's look at what happens with rotations, okay? So rotations tend to be, m over ei, and when you integrate, you get a length unit on there, okay? So let's see from a units perspective, what does that look like? So we've got foot kips times feet up here, and on the bottom, we have kips per inches squared times inches to the 4th. Does that make sense? Okay. Let's simplify this. What's feet times feet? So we get kips times feet squared. And on the bottom, we get kips times what? Inches squared. Okay. So we're left with foot squared over inches squared. That doesn't make sense, right? That's not degrees. Sorry, foot. Okay. So how do I get foot squared? Here, let's do this. How do I get foot squared over inches squared into degrees? How do I do that? Well, maybe the first thing I'll try and do is this. What were to happen if I did 12 inches per foot, 12 inches per foot? What would happen if I did that? all the units would cancel out, right? So if I were to just stop here, what would my answer be in? Remember, it's a rotation. So if the feet cancels and the inches cancel, this would be in radians, right? But if I want the answer in degrees, what do? I say, that. Does that make sense? So what is our conversion factor for rotation? It's 144 times 180 over pi. Does that make sense? Are we doing on time? Don't want too long. Okay, we're almost there. Does that make sense? Everybody with me so far? Okay. So what did I do right here? So if I take rotation, which is going to be in a unit ml over EI, and I carry it out, I get foot squared over inches squared. With deflection, instead of foot squared over inches squared, I get foot cubed over inches squared, because there's another length unit on there, right? So we have a problem here that we need to deal with. So how do we handle this? So I'll walk you through this. So this is what we got. So our desired units for slopes and rotations are in degrees, and our desired units for displacements and deflections are in inches. So what did I do for rotations? 12 inches per foot, 12 inches per foot, 180 degrees over pi radians. With me so far? So this is my conversion factor. For displacements, what I do is I do 12 inches per foot, 12 inches per foot, and then another 12 because I've got foot cubed. And what is 12 times 12 times 12? That times that is 144, times 12 is 1728. So these are my conversion factors. And so this is definitely another formula sheet addition. That for rotations, our conversion factor is 144 times 180 over pi, and for displacements, it's 1728. Why 1728? Because it's 12 cubed. Yes, sir?
Where did the radians come from? It looks like it's unitless.
Well, that's a great question. That's a great question. So the question was, where did the radians come from if it's unitless? So if I'm measuring an angle, okay, let me ask you this. So where did my eraser go? Okay. Can I erase this? Okay. What's the measurement of that angle? 90 degrees. How would you express the measurement of that angle in a unitless fashion with no units? It's pi over 2. Radians are unitless. Like when you plot the sine function, for example, like here's the sine function, right? This is pi. This is 2 pi, right? Those are unitless, right? But from an angular perspective, whenever something is unitless, we express that in radians. Like a unitless quantity is radians. The only reason of putting the term radians on there is to recognize that when we're looking at a number, if we use the term radians, that means it's a degree. Does that make sense? So from trig, any unitless angular measurement is in radians. That's what radians are. Is everybody else okay with that? All right. So what we're going to do, I think I'm actually at my very last slide. I am. So I did a lot of stuff today, a lot of theory. I want to let that seep in, and on Monday, as is my mode in this class, we're going to take it slow. We're going to start off with easy problems, and then ratchet it up. Okay? Sound good? I will see you all next week. Y'all